Hello, welcome to CSC7013, Advanced Math for Computer Scientists. This is Brady Chen. In Module 9, we discussed some of the basic concepts, theorems, and the algorithms in number theory. One of the important concepts is the divisibility. And also, we discussed Euler's algorithm, which is used to calculate the greatest common divisors. And also, we introduced the modular addition and multiplication, the prime numbers. The prime numbers are very important in number theories, and it's also very important in this module, in the module that we're going to discuss, the encryption and decryption algorithms. Okay, in part A of module 10, we're going to present an overview of the basic principles of public key crypto systems. A public key crypto system is one of the important applications for the number theory. So we will explain the two distinct uses of public key crypto systems, and then we will list and explain the requirements for a public key crypto system. Then, in part B of module 10, we're going to present an overview of the RSA algorithm, which is a very important public key algorithms. In part C, we're going to summarize the relevant issues related to the complexity of the algorithm, the RSA algorithm. And then we're going to provide a real case, a real example of the RSA algorithm. Okay, now let's first actually provide some overview of the general encryption algorithms. Now, there are basically two types of encryption algorithms. One is the conventional encryption algorithm. Now, in conventional encryption algorithm, you typically have two parties. Okay, you have two parties, sender and the receiver. Now, when sender tries to send some kind of message, and then the sender going to actually first send a message we call the plain text, and the message is going to be mixed with the key, and the key is kind of a secret, sequence that only the sender will actually know. So then the message then mixed with the key using the something called encryption algorithm. We use E, and then we send out something called the ciphertext or encrypted message. Encrypted message. So then we send the message to the receiving side. Okay. Now, in the receiving side, there is also an algorithm called the decryption algorithm. We use D. So the decryption algorithm going to decrypt the message based on the encrypted message or ciphertext, and the key. So the ciphertext and the key combined using the decryption algorithm, then we can actually restore the message back to its original format, the plain text. And then the receiver going to receive the message. Now, in conventional encryption and the decryption algorithm, both the sender and the receiver use the same key. So that's why in conventional encryption, decryption, they use the same key. So we mostly call these symmetric encryption, decryption. Okay. Now, in this module, when we try to apply the number theory, we are going to use the encryption with public key. Okay. So that means, typically, the sender and the receiver going to use different key. In fact, the sender going to generate a pair of keys. Okay, a pair of keys. One is the public key. It's called a public key. The other one is called a private key. So each user, the sender or the receiver, they're going to actually create their own pair of keys. Okay. So in this case, now we have two people. One is Bob. Bob is supposed to be the sender. And we have Alice supposed to be the receiver. So Bob is going to create its own public key and a private key. And then we normally use PU to represent the public key. Since this is actually key by Bob, so we're going to use PUB. Okay. And then the private key, typically we use PR. Since that's Bob's private key, we use PR, PRB. The B is a subscript. Now on the other side, we have Alice. Okay, Alice is gonna also create her pair of keys. Now that includes the public key, PUA, that's Alice, and the PRA, the private key for Alice. Now, in this diagram, so if Bob wants to send a message, which is actually typically a plain text input, okay. Now, we use X to represent the plain text. And then you're going to go through the encryption algorithm. Okay, so that's the algorithm. But before actually, Bob wants to send a message to Alice, right? So Bob wants to send a message to Alice, and then Bob is going to actually combine the plain text with the public key for Alice. Okay, so since this is Alice's public key, so Bob can easily get that key because Alice's public key is open to everyone. Same as Bob's public key. It's actually for everyone. So everyone can have access to Alice's public key. So Bob wants to send a message to plain text message X to Alice. So Bob grab Alice's public key and combine the plain text message and Alice's public key, and using the encryption algorithm, the public key encryption algorithm. So then it just generates something called a ciphertext, which is an encrypted message. Now, so we can use this, represent the encryption algorithm as E, like a math function. So we can, the E is represent like a math function. And then the E gonna take Alice's public key and the plain text that Bob wants to send to Alice. That's why. That's the ciphertext. So the ciphertext is generated by the function E, which is the encryption algorithm, with the parameter. The first parameter is public key for Alice, and also the plain text Bob wants to send to Alice. Now, when Alice receives the message, so Alice is going to use the decryption algorithm. Okay. Now, when Alice uses the decryption algorithm, it's going to take the Alice's private key. Remember, the private key is also generated by Alice, so it's accessible to Alice. But hopefully, the private key should not be seen by anyone else. It's only actually the private key for Alice. So Alice is going to use the private key and the ciphertext that the Bob sent to Alice. So then it's going to generate the message, and this is supposed to be the plain text. Okay. So so in math, we can write this as D, which is the decryption algorithm, and it takes two parameters. One is the private key for Alice. The other one is the ciphertext sent by Bob. And hopefully, this decryption algorithm is going to restore the message back to X. That's something that the Bob just sent. So that's the plain text. So here, Bob actually used the public key of Alice's public key, and encrypt the message and send to Alice. Now, hopefully, no one can actually decrypt the message Y. Okay, no one can decrypt Y except Alice, because Alice has her own private key. Okay, now if you want to decrypt the message, you have to get Alice's private key. Now, there are two basic types of cryptographic systems. The symmetric system, or sometimes we call the private system. Now, the other type of system is called asymmetric system, or many times we call the public key system. Now, the symmetric system is also called a conventional system. Okay, now in a conventional system, so we have two parties, sender and a receiver. Okay. Now, if the sender wants to send a message, and many times we call these plain text message. The sender need to combine these plain text message, or sometimes we call X, with a key. And this is a private key. Okay. So the plain text mixed with the private key through the encryption algorithm. Okay. Now this is going to generate something called a ciphertext. Okay. The ciphertext is the encrypted message. So the third party may not be able to see it if they don't know the key. Okay. So then the ciphertext is sent to the receiver. Okay. Now, on the receiving side, the receiver also uses a key, and it's a private key. Now, in this conventional or symmetric system, the key used by sender and receiver are the same key. Okay. So now, on the receiving side, you have a ciphertext and also the private key. So these ciphertext and the private key mixed up through the algorithm called the decryption algorithm. And hopefully, you can actually restore to the original plain text, so the receiver can read the message. So the ciphertext is the encrypted message. So normally we call it Y. Okay, so if both sender and receiver keep the actual private key secret, and then it's so difficult for the third party to decrypt the message, decrypt the ciphertext message. Okay, so that's conventional. Now, in this module, we will focus on the public key encryption. Also, it's an asymmetric system. So it's kind of different from the conventional one. Number one is for public key encryption or decryption, both the sender and the receiver use two different keys. Okay. So here's the scenario. For the sender, and in this particular case, we call it Bob, and the receiver, we call it Alice. When Bob wants to send a message to Alice, okay, so first thing we need to do is we have to make sure that both Bob and Alice are going to create their own pair of keys. So for Bob need to create a pair of keys. One is called a public key, and we use PU, and then we use the subscript B, which represent Bob. Okay, so that's a public key. And Bob also need to create a private key, PRB. So that's the pair of keys Bob need to create. And the same thing for the Alice. So Alice need to also create her pair of keys. One is the public key for Alice. The other one is private key for Alice. Okay. Now, for Bob need to create his public key and a private key, and Alice need to create her own public key and a private key. Now, each one needs to make the public key public, which means they need to make sure that their public key are accessible by everyone. Okay. So here, when Bob wants to send a message to Alice, so then Bob need to, suppose that's a plain text message. Okay. And that's X. So Bob need to encrypt with the key. Now that key is Alice's public key. So when Bob wants to send a message to Alice, Bob need to grab the public key of Alice. Okay, so that's PUA. Now how could Bob get the PUA? Well, it's public key for Alice, so everyone can get the PUA, not just Bob, everyone. Okay, so Bob wants to send a message to Alice, so Bob need to grab the PUA and then use the encryption algorithm. So mix the plain text and the Alice's public key. So this is going to generate a ciphertext. Okay, so now if we treat the encryption algorithm as a math function, so we call it E. So basically, when Bob wants to create a ciphertext, Bob needs to have the public key of Alice and the plain text, and then apply on the function E. So you use a PUA and X as the parameters for the encryption function, encryption algorithm. and then you generate the ciphertext Y. Okay. Now then you send the Y to Alice. Now when Alice received the Y, which is the ciphertext, so Alice then can use her private key. Okay, use the private key and also the ciphertext sent by Bob, and then use the decryption algorithm. So now if we treat the decryption algorithm as a function, again, just like an encryption algorithm, so then you can say, okay, so then I call the decryption function, and the parameter I'm going to use is the ciphertext sent by Bob and the private key of Alice. And then hopefully this decryption function is going to be able to restore the plain text message, which is X. Okay, that was the X sent by Bob. Now here's the question. Now, can we actually, make the message secret? The answer is yes. Because if Bob wants to send a message and Bob just wants the message to be seen by Alice, not everyone else, then Bob uses Alice's public key. Why? Because only Alice has her private key. If other people don't have Alice's private key, they cannot decrypt Bob's message, the encrypted message. Okay, so this basically means that the public key and the private key for Alice, they are somehow related. So Bob used Alice's public key to encrypt the message, and Alice has to use her private key to decrypt the message. Okay, so that's basically the key for the public key encryption. Now here's another scenario. So we still use the public key system, but in this case, when Bob wants to send a message to Alice, so here's the plain text Bob is using, that's X. Now what about if Bob send a message using Bob's private key? Remember, that's different, because in the previous slide, Bob sent Alice the message using Alice's public key. So then, once the message is encrypted using Alice's public key, only Alice's private key can, decrypt the message. Okay, no one else can decrypt the message. Only Alice can use her private key to decrypt the message. So this way, Bob can actually we can guarantee that Bob's message will be seen by Alice only. Okay. Now this is another scenario. If Bob encrypt the message using Bob's private key. Okay. So Bob's private key and X encrypted using the encryption algorithm. Now this is going to generate a ciphertext. So the ciphertext basically use the encryption algorithm, or if we interpret this encryption algorithm as a math function, so it's the function E. And the parameter the function going to need is first the plain text. The second one is the private key of Bob. So Bob uses his private key and try to encrypt the plain text, and Bob generate the ciphertext, and then Bob send the ciphertext to Alice. Okay, so when Alice received this ciphertext Y, Alice wants to decrypt the message. Now what Alice is going to do? Because the message was encrypted using Bob's private key, so now Alice has to pick up Bob's public key to decrypt the message. Okay, so that's Bob's public key. Okay. So that's a decryption algorithm. So the math function you can use to reinterpret D as a math function D, and then the parameter is Bob's public key and the encrypted message, the ciphertext sent by Bob. So hopefully this is going to restore the message back to the plain text that was sent by Bob. Can we keep the message secret in this case? You may ask that question, right? The answer is no. Why the answer is no? Because Bob encrypted message use his private key. So Alice decrypted message use Bob's public key. Now the problem is Bob's public key is not a secret. It's not a private key. So it's basically open to everyone. So if everyone wants to get the Bob's public key, they can. Okay? So that means when Bob actually sends the message, encrypt the message to Alice, Alice can decrypt the Bob's message by using Bob's public key. But someone else can do the same thing. Everyone can do the same thing, because if for example, Kathy. So if Kathy find this ciphertext, and then Kathy can grab Bob's public key, and Kathy can also decrypt the message and get the Bob's message. Okay. Now, your question may be, what's the point of this encryption with private key, with Bob's private key? Why? You cannot keep the message secret. What's the point? Now, this is actually another application. That's a different scenario. In that scenario, so this scenario is called authentication. Authentication. Now, while you cannot keep the message sent by Bob secret, however, there's one thing you can be sure is that if you can decrypt the message Y sent by Bob, if you can decrypt the message and you can successfully restore the message to X, then you are certain that this message was really sent by Bob. Right? The message was really sent by Bob. Why? Because this encrypted message can be decrypted using Bob's public key. Now, the only message can be decrypted by Bob's public key is the message that was encrypted by Bob's private key. Now think about this, right? So if a message encrypt a message, then the message can be decrypted using Bob's public key. Okay, and then you get the message X, and that message must be the message sent by Bob, because any message that can be decrypted using Bob's public key must be encrypted using Bob's private key. Okay, now who can encrypt the message using Bob's private key? Only Bob, right? That's the assumption. Unless Bob's private key is compromised, so then someone else can fake Bob's ID and send message and pretend he or she is Bob. But otherwise, if the Bob can keep the private key in a safe location, then we are pretty sure that if the message can be decrypted using Bob's public key, then that message must be sent by Bob. So that's That's called authentication. Authentication also is very useful. Now, one of the example is, for example, if, for example, the president of the United States, he wants to, send a public message, or broadcast a message to the audience. Now, if he used or she used the encryption with his or her private key and broadcast to everyone, so everyone can grab the president's public key and then restore to its original plain text. And we're sure that's the message coming from the president, right? So otherwise, if president sent the plain text without any encryption, then everyone received the message, and someone can fake the president's ID and send, forward the message, because everyone can see the message and fake the ID. So now, using the authentication, then you can be sure that this message was really sent by the president, because otherwise I cannot use president's public key to decrypt the message. Okay, so that's the other scenario. So using the public key system, you can actually, you have a flexibility. You can either use the other side's private key to encrypt the message, so then the receiver can actually decrypt the message, or you can use your own private key to encrypt the message and send out, and everyone can use your public key to decrypt the message. These are two different applications. So we listed here the differences between conventional and the public key encryptions. Okay, so in the conventional, the same algorithm with the same key is used for encryption and decryption, and the sender and the receiver must share the algorithm and the key. Okay, so now for the public key encryption, so one algorithm is used for encryption and unrelated algorithm for decryption with pair of keys, one for the encryption and one for the decryption. Okay, and the sender and the receiver must each have one of the matched pair of keys. Okay, now typically these keys, one is called a public key, the other one is called a private key. These are typically not the same key. Okay, to make the message secure or to perform the authentication, now you have to make sure one of the two keys must be kept a secret, and which is called a private key, and you can publish the other key so everyone else can access the key. Okay, so one public key, one private key. Okay, now typically it must be impossible, or at least impractical, to decipher a message if one of the keys is kept a secret. So that means if Bob created its own public key and private key, so if someone, of course, everyone can get the public key, Bob's public key, right? Now, hopefully, this key must be somehow related, because one can be used for encryption, the other one can be used for decryption, right? So they must be related. But however, it should be very difficult for the third party to find out the private key if they know the public key. So that means based on the information of the public key, they cannot get the information of the private key. That's a requirement. That's something we try to resolve using the knowledge which is built in the number theory. Okay, so that's why we actually, talk about the basic of number theories. Okay, so in what follows, we only actually focus on the public key encryption. So we are not going to do anything related to conventional encryption. So if you are interested in conventional encryption, get a book, get a cryptography book and find out the details of conventional encryption. But in here, we're going to talk about the public key encryption only. So let's summarize what we talked about in the previous slides. Okay, now we talk about the first scenario. Well, the sender, we call source A in here, and destination. So suppose that's the message the sender want to send. Okay, the message we use X. Okay, that's the plain text. And then we use the encryption algorithm, and we call it E, right? So then, if we want to actually encrypt the message, use the public key of the receiver, the destination B, right? So we can use the public key of the destination B and the plain text. Then we get the ciphertext, which is actually E. If we think about encryption algorithm as a math function E, and then we use the plain text and the public key of the destination B. And that's the ciphertext. Now, when the receiver receives the ciphertext Y, and the receiver going to use the decryption algorithm, and the decryption algorithms are related. They are not necessarily the same algorithm. Okay, it's similar. They are similar, but not necessarily exact the same. Now, the decryption algorithm is going to use the ciphertext Y, and the private key of the destination B, the receiver. Okay, so then we actually create the D, that's the treat it as a math function, and then the private key of the B and the ciphertext, and hopefully we can restore to the original message X. Okay, now we just mentioned that we can actually secretly send a message to the destination, and we call these the confidentiality. Now here's another scenario. That's the authentication. Again, we have a sender, which is a source, called source A, and destination, receiver. Okay. Now, if the sender wants to send a message to the receiver, okay. Now, sender can use the encryption algorithm and mix the plain text X with the private key of the sender, which is in this case is A. Okay, PRA. That's the private key of the sender A. Okay, and then generate the ciphertext Y. So in here you can see that that's the encryption algorithm, and that's the private key of the sender, PRA, and the plain text. Now the receiver, when the receiver receives the encrypted message Y, receiver can actually use the public key of the sender. Now keep that in mind. If you actually encrypt it with a key, either public key like the previous scenario, or the private key like this scenario, like in authentication, then if you encrypt it with one of the key, either public or private, then the decryption has to use the other key generated by the same person. Okay, so that means, so the sender has a public key, PUA, and the PRA, the private key. So that's the pair generated by sender. If you encrypt using the private key of the sender, and you have to decrypt using the public key of the sender. You cannot decrypt using either the public key or private key of the receiver, which is destination B. You cannot do that. Okay, so then the decryption used the public key of the sender, which is PUA, and then the decryption algorithm. And so the decryption algorithm, use the private key, public key of the sender, and here is the ciphertext, the encrypted message, and hopefully this is going to restore to the original message. Like I said in the previous slide, this is for authentication, because there's no way you can keep the message secret, because everyone can grab the public key of the sender, PUA, and decrypt the message. So everyone can see the message, but the only thing in this case, the only purpose is to make sure everyone is confident that this is the message that's sent by the sender. Okay, now this is the third scenario using public key crypto system. So in this third scenario, we're going to use the encryption decryption twice. So in this case, the sender going to encryption twice. First, use the private key of itself, and then use the private key of the receiving side. And on the decryption side, you're going to decrypt twice. Okay, so in this case, to send a message, you need two keys. And to decrypt the message, you need two keys as well. So basically, you're gonna need all four keys to perform the job. So in that case, so the source A or the sender A gonna actually create its own pair of keys. One is the public key of A. The other one is a private key of A. Okay. Now on the receiving side, the receiving side also needs to create a pair of keys. One is the public key, which is B, okay, and the private key of B. Now, when the sender tries to send a message X, which is a plain text, the first step, the sender going to use the encryption algorithm. Okay, so the encryption algorithm going to combine the plain text X and the private key of A, which is sender. So the sender used the private key, mix the private key with the plain text using the encryption algorithm. So using the math formula, we can say, okay, sender using the encryption. So then you're going to mix the private key of the sender and the plain text, and this is going to generate a ciphertext Y. Now, sender is not going to send the Y to the destination. The sender is going to actually apply the encryption algorithm again. Now, this time, sender is going to actually encrypt the ciphertext Y, a mixed Y with the public key of the receiving side. Okay. So that means, so the sender going to actually use the encryption again. Now this time, the sender going to use the ciphertext combined with the public key of the receiving side, which is destination B, right? So this is going to generate a Z, message Z. Okay. So then the sender actually sends a Z to the destination. Now, so when anyone who wants to decrypt the message, they first need to decrypt the message first to using, the private key of the destination to decrypt the message and restore to Y, right? Because you have an X and then you have an intermediate message, which is also a ciphertext. And that's the final ciphertext Z. So Y is in the intermediate ciphertext. So the first, you need to decrypt the message Z to the intermediate ciphertext Y. And then restore from Y to X. Okay, so when the receiving side received the message Z, then it will use the decryption algorithm. Okay, the decryption algorithm will combine the ciphertext Z and the private key of the receiving side of the receiver. Okay, so because Z was encrypted using the public key of the receiving side. Okay, so when the second time when the sender actually encrypt the Y using public key of the receiving side. So when the receiving side receive it, so it will first use the decryption algorithm and using the private key of the receiving side and the ciphertext Z. And hopefully this is going to restore the message back to Y, right? Because the second encryption algorithm encrypt the messages Y, okay, and using the public key of the receiving side. So the receiving side can decrypt the message using the private key and the ciphertext Z. So now, hopefully, you're going to restore the message back to Y. So this message is still not decrypted. Okay. But don't worry. Why? Because you can do the decryption twice. Now, because Y was encrypted using the private key of the sender, Y was encrypted using the private key of the sender. So in order to decrypt the Y, so the receiving side are going to need the public key of the sender, right? Because encrypted using the private key of the sender. So to decrypt the Y, you just need the public key of the sender to the Y. And hopefully this will restore back to X. So you see the point here? You basically encrypt twice. First encrypt using the private key of itself, and the second encrypt using the public key of the other side. And so then the other side, when the other side received the message, the ciphertext Z, and it first actually decrypt once to restore back to the intermediate ciphertext Y. And then once you got the intermediate ciphertext Y, and then you decrypt it twice, and this time use the public key of the sending side, okay, the sender. Now this way, you can actually guarantee the authentication and the secrecy of the message. Okay, to summarize the topics we discussed in the previous slides, so we can actually use the public key crypto system to do three things. First, encryption and decryption. So if we want to actually send a message to the receiving side, you can use the receiving side's public key to encrypt the message and send to the receiving side. And only the receiving side's private key can decrypt the message. This way, we can guarantee the secrecy of the message. That's an encryption. And also, we can use the public key crypto system to do something called digital signature. Okay, so that means the sender signs the message with its private key. So that means the sender encrypt the message. You can interpret this message as a signature. So I used my private key to encrypt my message and send it out. And then to see the message, to see the signature, you just grab my public key, right? So everyone can grab my public key. Okay. Now the third case, so you can actually keep the authentication and also keep the secrecy. And then you can actually create some kind of scenario called key exchange scenario. Two sides cooperate to exchange a session key. That's something, another application. Okay. Now, why we want to do this? Because in the third scenario, remember, we encrypt the message twice, right? The sender, receiver, you encrypt the message. Okay, first use sender's private key, right? Okay, and then, so that's the original message. And then use receiver's public key. Okay. And then you got a Z, right? And when the receiving side received the message, then that's encryption. And the receiver gonna first use the private key to restore back to Y using decryption algorithm. So these are paired. Okay. Now once you got a Y, then you can decrypt again using the sender's public key. Okay, so you restore to X. So you pair these two, right? So you basically use all 4 keys. Okay, so you can actually send a message from the sender A to receiver B. Okay. However, these encryption algorithm is very, very inefficient. You can technically send a message, any plain text message, to the destination. Okay. However, if you want to actually regularly send a message like all the whole messages, this is going to be very slow and very costly because the encryption, you can encrypt twice, you can decrypt twice, so it will be slow. So that's the reason why people only use this to send a very small message, such as the key. Okay, so I'm gonna say, okay, let's say sender A and receiver B wants to communicate. Okay, and then sender A say, let's actually communicate with a private key. So I generate the private key and I send the key to the receiver. So then both sides are going to start to use the symmetric algorithm instead of, that means the conventional algorithm, because conventional algorithm with the same keys, these are very, very fast, very, very efficient. But the public key crypto system are very flexible, but they are very, very slow. Okay, compare with the conventional one. They are very slow. So they only use the to exchange the keys. Okay. Okay. Now, in order to make the public key scheme works, we have to make sure the public key, crypto system meets certain requirements. Okay. Now, here are the conditions that we must actually meet to make sure the public key encryption actually works. Okay. So number one, we have to make sure it is computationally easy for party B, okay, to generate a pair of public key and a private key. Remember that in order to do the communication, we say that for both sides, you need to create a public key and a private key, a pair of keys, right? One is PU for source A, one is PU of A, and the other one's PR of A. Now these two keys are related, but one should be make public, the other one is keep secret. And they are related, they should be easy to create. Okay. Now also for destination, it also requires to create a pair of keys. Okay, so the public key and the private key. Now it should be computationally easy for party B, okay, to generate a pair of keys. Also, it should be computationally easy for party A to generate a pair of keys, right? It should be easier for everyone to generate a pair of keys. Okay, that's one requirement. Now, the second requirement is it's computationally easy for sender A, knowing the public key of, which is PUB of party B, and the message to be encrypted to generate the corresponding ciphertext. Okay, so that means it's computationally easy for sender A, knowing these plain text and the public key of B. Now, using the encryption algorithm, it's relatively easy for source A to generate a ciphertext Y. Okay, so it's computationally easy. Now we're gonna explain what does computationally easy mean. Okay, it should be fairly easy. Like it just take like maybe a couple of milliseconds to complete this job. Okay. Also, it's computationally easy for the receiver B to decrypt the ciphertext Y using its private key PRB to recover the original message. So that means it should be relatively easy to use the decryption algorithm, knowing the private key of the B and the ciphertext, and decrypt the message to restore it to the original plain text message X. So when we say computationally easy, it means it should be very quick to do so. Remember, in previous modules, we just talked about, when we check the primarity of a number. So if we use the traditional approach, try to actually divide the number by every number smaller than it, and make sure there's no fact that other than one and itself. So so that means to check the primarity of a number, you have to do a division. So from 2, 3, 4, 5, 6, all the numbers, all the way to half of this number. So we know that if this number is so big, it's computationally infeasible to do the checking. Remember the example? It will take like a 10 to the 90 years to do the job, right? I forgot the actual number, but it will take actually more than million billion years to to test a primarity of a number. That's basically called computationally infeasible, even though theoretically it's always possible, but it's computationally infeasible. So when you say computationally easy, that means it should be very quick to do the job. Now, the other condition is that it should be computationally infeasible for an adversary. That means when an attacker, okay, try to attack these, message. So when the adversary, if they only know the public key, then it's computationally infeasible to determine the private key. So even though, we create the public key and the private key pairs, okay, they are related. But since the public key is always open to everyone, so it should make it extremely difficult, make it computationally infeasible for anyone who can find or somehow determine the private key, knowing the public key. Only by knowing the public key, it should be able to determine the private key. That should not be computationally feasible. Okay. So then technically we can assume that there's no way for people to find the private key if they only know the public key. So that's what this statement says. Also, it should be computationally infeasible for an adversary knowing the public key and the ciphertext to recover the original message. Remember, if the reason why the receiver can easily restore the message from the ciphertext is the receiving side has its private key, right? PIB. So using the PIB and the decryption algorithm, it should be easy to, decrypt the message and restore to X. Now, if they don't know the private key, they should be not impossible, but computationally infeasible to do so. Now, what's the difference between impossible and computationally infeasible? Now, impossible means no matter how much time effort you actually put in, it's always impossible to, decrypt the message. Now, computationally infeasible means even though in theory you can decrypt a message, but it will take you like 1,000,000 years or 1,000,000,000 years to do the job. That's computationally infeasible. Now, practically, even actually you can take like 1,000 years to decrypt a message. That's computationally infeasible, right? No one's going to wait for 1,000 years to decrypt a message. So if you know the ciphertext and only know the public key, you cannot decrypt a message. The only time you can do the job is you also know the private key. Okay. So if we meet all these requirements, there's one more. The two keys can be applied in either order, which means once you create a pair of keys, you can make one public, the other one private, or vice versa. You can make the other one public, the one, private. So either way, you can just the two keys. You can make one public, one private. Okay. So that's the requirements. If some of the requirements are violated, then the public key encryption algorithm is no longer safe. Okay. Okay, here's the last slide for the part A. So basically, in order to actually do this, this is actually almost like in math, we try to find a one-way function. Okay, so if we treat the encryption algorithm as a function, so that means So you can actually go in one way, and it's so difficult to go in the opposite way. What does that mean? So that means, so we need something called a trapdoor one-way function. A one-way function is one that maps a domain into a range such that every function value has a unique inverse, with the condition that the calculation of the function is easy, while the calculation of the inverse is infeasible. So that means, now in most cases, you can actually, say, okay, I have a message, like a original message, apply to the function f, I got a y, right? So the calculation of f of y is so easy. And then hopefully, then you can actually say, once I got y, how can I restore to x? Then typically people use a function called the inverse function, f to the minus 1. That's an inverse function. And then in most cases, the function and the inverse function are just a function pair, so they can easily exchangeable. So, but in order for the public key encryption algorithm to work, we need to find some kind of function that it's so easy to calculate f of x, but it's not easy to calculate the inverse. So in this particular case, like an encryption algorithm, we can actually define a function f and also a key. Okay, so now you can actually easily calculate the f of k of x. So that means the function f and also the original variable combined with the key, and you can easily calculate y. Okay, so if k and x are unknown. Okay, now however, the opposite is also should be easy if k and y are known. Okay, now if k is unknown, then it should be very, very difficult to calculate f of k inverse y. Okay, so that means the key is important. So that's really something we want. We want a function f of k, fk of x. We want fk of x. And it's so easy to calculate this to generate normally the ciphertext y. And also, it's also easy to calculate the inverse of k if we know the k and y. But if we don't know k, then this isn't difficult to do. Okay. So how can we create such a kind of function? That's something we're going to talk about in part B. We're going to use all the knowledges we used in the previous module, module 9. That we use the modular operation and the format theorems, and we're going to use all these primarity properties. Then we can create some kind of algorithm that use some kind of a one-way function to perform this public key encryption, decryption algorithm. That's something we're going to talk about in part B. Thank you.